Today I am going to talk about something which is at some point in uh, as a life, everyone would have been taught. Those who are interested in physics, or even those who have heard about Einstein, would have thought what is so special, that why Einstein was the only first physicist, theoretical physicist, to get the Nobel Prize. But actually, many of them confuse that he got Nobel Prize invent inventing theory of relativity. But actually, he got Nobel Prize for discovering the photoelectric effect. So, but still, this theory of relativity, special relativity and general relativity, remains it is still valid, and still there has been no good theory which is able to explain the laws of motion. So now let us see why we have to look, why there was need to look beyond Newton, and also why it is what was there, what Newton did and what he couldn't explain. What Newton achieved was a great, but why Einstein achieved was even more beyond his time. So let us see that. So for that, we have to understand why we need to look beyond Newton. Why? So we all would have read in class till class 12 about Newton's laws of motion. Everything, some problems or any, all the three laws, and also so many questions or so many kinds of motion, etc. But I want to begin that we have already seen that light behaves like particle as well as wave. So this took so much time for then scientists to understand this behavior, this peculiar behavior of light. Because in some experiments it used to behave like a wave, and in some experiment it used to behave like a particle. So it was really, scientists were so much confused, or could not explain, because they thought that particles and waves are different and they cannot be existing together. But that kind of behavior has been exhibited by light, that sometimes it behaves as a particle, sometimes it behaves as a wave. Like diffraction is when it behaves as a particle, and interference when it behaves as a wave. So Newtonian theory was able to explain most observable phenomena, but few of the things which it couldn't explain was the anomalous orbit of Mercury. Okay, the orbit of Mercury was a little different from the other orbits of the planets. Let us not look more into it, but understand that that orbit of Mercury was not accurately predicted by Newton. And then all the electromagnetic waves travel with speed of light in vacuum. Why? Newton could not answer this. And wave particle duality, as we know, Newton could not explain a wave particle duality of electrons and light, that is photons. And then classical physics couldn't explain the spectra emitted by different atomic elements. Like each element in the periodic table has its own spectra, which was not explained, cannot be explained by Newton's theory. And also, when the speed of light, when the speed of motion is comparable to the speed of light, Newtonian mechanics failed to match the experimental results. So there was so much deviation from the measured results and the predicted results. Where does the gravitational force come from? Like it doesn't answer that question. It only assumes that gravitational force is law of attraction and a square law dependence, inverse square law dependence between the distance of the two objects or many. two masses. So where does another thing is ferromagnetism and then superconductivity. Superconductivity is the resistance is zero at some point, and that is uh, it is unbelievable. Like it is one of the superconductivity is used in many places now. So now let's look into the Newton's theory and examine why it couldn't explain microscopic phenomena like behavior at the atomic scale, and also as as well as the motions which have velocities which are comparable to the speed of light. That is the ratio between the speed of the object and divided by speed of light is less than 1. We know that. But often in Newtonian mechanics, it is only valid when the speed of motion is very much less than speed of light. So that is what mentioned. Like everyday objects in everyday life, we never reach to the speed of light. For example, even if we go at 100 kilometer per hour, 100 km/h, then it is not even close to the speed of light or not even comparable to the speed of light. So and then what happened was in the start of 20th century or by the end of 19th century, everyone thought that almost like physics is over. Then what is there? Then two people, Max Planck and Albert Einstein, have almost have challenged the physics community at the start of 20th century, which eventually led to the development of two remarkable theories like Max Planck's that everyone would have heard at least of Planck's constant, which was named after him in the light. So one of the things was that due to Planck making an assumption that what if light is only a chunk of matter, like it only allows some discrete levels of energy. That's assumption to explain the black body radiation, which led to the eventually led to the development of quantum mechanics. Everyone know that Schrodinger was pioneer of development of quantum mechanics, and later other theory was other theory was making in shape, which was in other direction. In the microscopic scale, quantum mechanics was developed, and at the macroscopic scale, where the in the interstellar space or in the outer space, when velocities are much of stars and other outer space bodies in the universe who have velocities almost close to speed of light, are then those kind of topics were covered by in theory of relativity. Special and general, two theories were developed by only Albert Einstein. So it was remarkable that one man, Albert Einstein, has developed a whole theory of relativity, shook whole physics community, and they could not believe it until the theory of relativity was proven. It took some years to prove it, and also a lot of effort to prove it. And I do that is a topic of discussion for another day, like how it was proven, and also about the Michelson-Morley experiment. You would have heard it somewhere. But that experiment led one of the starting points that something is there which the physics were missing. So now the special theory of relativity here, I firstly special theory of relativity is special. It is only a part of general theory of relativity. Like it is not generalized. It is only a special case where only deals with the description of events by observers in inertial frames of reference. That is, the motions of objects may be accelerating with respect to the inertial frames, but the frames themselves are unaccelerated. Now, I don't want to go into, you will look into what are inertial frames and other things, objects, and what are the observers, what is the event. These are things you will look into it more closely, because you would have been already studied somewhere. But now we need to look into what is more obvious more closely, because no one thought that those obvious things which were thought as obvious, uh, which were questioned by Einstein, and that obvious things which were thought to be obvious eventually turned out they were not obvious, and that's why it led to theory of relativity. And why I'm talking like this is that the obvious thing is, we will look in some time. Now, the general theory of relativity, which we are not going to discuss, of course, here, it, it is with frames of reference, like all frames of reference. It will generalize to all frames of reference. So, including non-inertial ones. So now, some of the questions which the reader or the viewer of this video may have: what is an event? We all know, everybody would have been known that at least some idea, like what is an event, something happened, what is an event, who are observers, what is inertial frame of reference, how Newtonian mechanics deals with non-inertial frames. And these are the most important questions, some basic questions which need to be answered. And then remember that one point is, Newton's laws only hold good in inertial frame of reference. So now we all know these things. Now, along with those questions, in next few lines, we are going to assume that to have few questions to ponder again, after knowing the implicit assumptions, that which I mentioned, that obvious things which aren't more obvious, implicitly assumed, like they are not stated, that they are assumed. That is, time and space interval measurements made in classical physics are absolute to all frame of reference. Then we will look into it very deeply. But for now, what is this? Time interval and space interval, we thought it is absolute to all frames of reference. Like it is independent of everything. Now, length, mass, and time, the three basic quantity in mechanics, are all independent of relative motion of measurer. So even if the observer is moving or static, or is moving with zero velocity or standing still, the length, mass, and time, that MLT, which we use in units and dimensions, are some three basic quantities which always are independent of the motion of the measurer. So that is one of the implicit assumptions. Don't you find it interesting that when we are reading this Newton mechanics, we never thought all these things. We all observe this world and think that everything is so obvious. But that is the difference between, uh, what to say, that only that difference which not only us but even so many physicists couldn't find out till Einstein thought about it. Then the acceleration of particle is the same in all reference frames, which move relative to one another with constant velocity, since mass is unaffected. So we assume that mass is always unaffected by the motion of reference frames. Like mass is a constant in Newtonian mechanics, it doesn't change. But we all know that, we have read at some point that electron has something called as rest mass and moving mass. So that is one of the results of relativity, and why we'll look into that. Then hence the product MA will be same for all inertial observers. So that is what we know, that we know that F is equal to MA is taken as a definition of force according to Newton's second law, will be same for all inertial observers. So these are the things, like some assumptions which led to some conclusions, and we need to look into it, that these implicit assumptions are not there is some problem with these assumptions, and that's why it led to theory of relativity. Conclusion is that Newton's laws of motion and equations of motion of a particle be exactly the same in all inertial systems. So what is the conclusion of this much time? That Newton's laws of motion and the equations of motion of a particle be exactly the same in all inertial systems. So this is just stated here why I was giving the build up to this, uh, whatever is up to why we need to look beyond Newton. This is why we needed to look beyond Newton. That now we have looked what are the things we have, some anomalies we looked which Newton could not explain, and also what are some implicit assumptions and the conclusions arising from that, uh, in from the Newtonian mechanics we saw. But now you will be we will look into why uh, it is wrong. What is wrong with Newtonian mechanics? So that we will continue in the next video.